My name's Nicholas, and I am a software engineer here at Monzo. So today I'm going to talk about data races. So has anyone seen this warning message before? Hands up for anyone who's seen this. So you've found the race detector. So Go is a new language that has a lot of promise in the concurrency. So Go routines, which are lightweight threads, are very easy to spawn. So you just need to put the Go keyword in front of a function call, and there you have Go routines. So why don't we just make everything Go routines? Because Go routines are so awesome. What can possibly go wrong? So since I'm here talking at a bank, let's try to implement a withdraw money functionality. So this is a code that um, just that I've written to implement a bank account. So you have a withdraw function, and you give it an amount, and then it will deduct the amount of money from your balance. And of course, we wanted to make sure that the balance don't go negative. Otherwise you just lose money. And so if we try to run this program in four Go routines, can anyone guess what the output will be? What is it? Yeah, exactly. I was going to show run this code, but maybe I can't do this in the web slides. But the thing is, even though it looks like what we're expecting would be something like this. So you have three threads with three different withdrawals. What you want to happen is one of the threads read the balance, checks that it's not less than your balance, and it reduces the amount from a balance, and then the next thread goes and do the same withdrawal again, and then you get to the third Go routine, and then the third Go routine will say, well, there's not enough balance, so it doesn't let you go negative. But if we run the program, sometimes it will give you a positive balance. Sometimes it will even give you a negative balance. And one of the reasons is because if you run the Go routines in concurrently, the Go routine doesn't respect the ordering of how you write in your program. It just runs it concurrently. And so if both all three of the Go routines start withdrawing from the balance, you see that it first checks that all the balance are £10. So you can deduce the amount. But when you do the actual deduction, it will actually read the balance again, and it's actually a different value. And because the reading and the writing are not synchronized, the output is non-deterministic, and therefore you can get a negative balance from running the program. And this is a symptoms of a data race. So perhaps you've heard of a data race before, and you already know how to fix it. Well, of course, there are many ways you can fix this program, right? You can use channels. So do not communicate by sharing memory. Instead, share memory by communicating. So you can use channels. You spawn one Go routine, kind of owns the balance, and then you make other Go routines talk to this one Go routine to deduce amount or get a balance update, so that you don't ever get into data races. Or you can use a mutex lock, so which gives a piece of shared memory mutual exclusive access to the shared variable, so that only one thread can write to or read from the balance at one time. So what happens is you lock the balance, you do the updates, you do the reading, and then you unlock it, and then the other thread will come around, and then the other thread can then access it in the same way. Or maybe even better, don't write concurrent code if you don't need to do anything concurrent. If you do it in a sequential way, no problem. There's nothing shared. There's no data race. But have you ever wondered why this can solve the data race problem? So we turn to this gentleman here, who some of you may know if you work in distributed system. His name's Leslie Lamport, and he's very well known for his foundation work on distributed systems. So Paxos, Lamport clocks, etc., etc. And we're going to turn to him to look at two of his very early ideas that can be applied to explain what is a data race. So first of all, we need a notion to talk about an ordering of events. In a very, very old paper in 1978, time, clocks, and ordering of events in a distributed systems. He introduced the concept of a happen before relation. It's not as complicated as it sounds because it's really straightforward. It's just if something happens before something, then it's exactly what it means. So notation-wise, we sometimes use the arrow to denote the happen before relation. So A arrow B means A comes before B. And so here we want to talk about the ordering of events, and particularly the reading and writing of shared memories. And the other idea that we want to look at is called sequential consistency. So this one I'll read it out. The result of any execution is the same as if the operations of all the processes were executed in some sequential order, and the operations of each individual processor appear in a sequence in the order specified by its program. A multiprocessor satisfying this condition will be called sequentially consistent. So this is, of course, in the context of multi-core programming, but it applies the same to concurrent programs as well. But in layman terms, this just means that the concurrent execution is consistent, or it appears to match some sequential execution. It is a very desirable property, and it is a very strong guarantee that you can give for a distributed or concurrent system. But what it does is it helps you to you can reason about a concurrent program like a sequential program much easier if you have this sequential consistent property in your systems. So what does this has to do with data race? So once upon a time, my colleague told me an anecdote that a data race is the only competition where if you come last, you win, because in a data race, the last thread or last Go routine that writes to a shared memory variable will win the data race, and it will have the value of the final write. But reading is fine because reading doesn't change the value. And we can visualize with a happens before graph. So apologize, I'm going a little bit technical here, but a happens before graph is just a way of expressing causality in a kind of more graphical form. So here I have the three original withdraw threads: withdraw 5, withdraw 4, and withdraw 7. And the RRW means read, write, just like in the original program where we first read the balance, and then we update the balance, so we have to do a read again, and then we do write. So the arrows here, again, represents the kind of happens before relation. So each of the thread happens after the program started, and then the program ends after all the three threads finished. But notice that there's no relation, no happens before relation between any of the three threads. And so, but within a Go routine, the happens before relation is sequential. So it follows the source code order. So the RRW in each of the Go routines will still be a straight line. So that's okay. So as you can see, there's no ordering between all the three Go routines. And so you have a data race. So they have to compete to be the last to write to the shared balance variable. So what does a no data race look like? So if, let's say, I implement the balance differently and I synchronize it with either channels and mutex lock, it is like going into a race but with match fixing. Because even though you're going into a race, the order that you get to execute is already predetermined when you are scheduled. So the event, so this graph is a lot more complicated. The events might appear in a different order, but it's always in total order, which means all the events that happen in one execution is always ordered. There's always one way you can trace back from the program start to the program end. So what I've highlighted in the graph is one possible execution. So as you can see, the program will start. It will call the withdraw 5 thread, and then it will call the withdraw 4 thread, and then withdraw 7. So there is a direct relationship between each of the read and writes. And because all the possible execution kind of can give the same result as a sequential execution of it, so this is kind of what we mean when we say sequential consistent. So you can flash out your concurrent execution and get a sequential trace of your program. And so this is what no data race would look like in a happens before graph. So maybe you're wondering, like, oh, why do I need to know all of this? Because this is really, really boring, really technical. But since a lot of you already know about the Go race detector, which you can run by using the dash race flag when you go run a program or when you go build a program, or you can also run tests with the race detector turned on with go test dash race. It's an amazing tool. So it works by taking your code. At compile time, it will instrument all your code. So all the memory read-write access will be instrumented. They will be given special instructions to keep track of what is being written and what address is being read from memory. And then it kind of analyzes the happens before graph as you execute. So usually you don't run the program with the race detector turned on because it will slow down your program a lot because it's doing all this calculation while you're running the program. And so if I take the code in my second slide and run it with the race detector, this is what it will look like. It will tell me that warning data race, something write as this address and previous write in this address. So it's actually really tracking all the read and write events in the program. And so it found a data race in here. So if you want to know a little bit more about the race detector under the hood, I would recommend this talk by Kavya which goes into a lot of details about how it works really inside the race detector. I don't have enough time to go into all the details, but yeah. So summary. Using concurrency correctly in any programming language, as always, it's really, really difficult. We can detect data races by analyzing the happens before graph of memory access. And do test your code extensively with go test race, dash race. If possible, do fuzzing as well. It's a great, but it's probably not the only way because I used to be a researcher and our team is currently working on something that will try to address data races detection in static time. But this topic of data race is just really, really big. And there are many more interesting and related topics like memory model and synchronization. And I think I'll stop here. If there's any question, please do come talk to me or ask a question now.
Yeah, anyone, just raise your hand. Do you want me to pass you over?
Does Go's race detector have any false positives or false negatives? So in other words, are there any cases where the race detector can show a race when there wasn't one, or when it doesn't show a race when there actually was one?
It depends on how you define them, but I think the answer is no, because the race detector works by instrumenting your code and then kind of building the graph as you analyzing the happens before graph as you run the program. So it will only report there is a data race when there is one that actually happened. So as for whether it will not detect anyone, I don't think so as well. No. Yeah, what he said. I didn't hear the question.
Yeah, so you mentioned your team is working on a static analysis of these graphs. So I was wondering, like, memory locations change over, when you run the code, and do you do predictions on these stuff, or like?
I'm glad you asked.
I'm sure there are papers out there. Nice.
So, well, it's a long story. The Go memory model is defined in terms of happens before that happens before relation between certain primitives in the language. It's not very complicated. But one of my team's PhD student is now working on trying to analyze race detection using types. So behavioral types specifically. So basically, you analyze the program, you extract a certain behavior of your program, and then you use that information to determine whether there's a race or not. So likely there will be more false positive than the actual runtime detection. But the advantage is, of course, you can avoid having them in the first place.
Cool.
Cool. Thank you, Nick.